next door apartment.
They robbed the mail truck.
I because you check your status online, and it says they have a chance to he's on registry. On registry, I didn't process that.
Dan Dunlop, who was Dan Dunlop was the president of NLA last year. He was the
Should be fine.
But I think, well, I gotta know.
He said, "You guys are engineers. You're obvious."
We just have to have it in by.
So
Yeah, you just have to. The trick is you have to just like get it in your stamp. Post office when you mail it, like actually like go up and give it to them. Because then when they hand cancel it, it marks it with the date. And so it'll be marked that you put it in the mail on that day.
I think I know.
Because if it's not, because then when they get it, they're like, okay, even if it's a few days after the election, they know that you sent. At least that's how it works for Alaska.
I'm not sure.
Oh yeah, you're Pennsylvania.
I've worked like 8 times everybody else's votes.
I remember these were.
I was thinking Indiana.
So.
No.
Yeah.
Because Indiana.
Yes.
All my friends are driving.
I need to. Alaska's got this like wonky like. Fill it out online and then it prints it out and then you mail it in.
Howdy, gents.
Oh yes, tomorrow. I haven't. I
I mean, he confirms your attendance.
So to the guys on Zoom, I sent a link to a Google Drive. Can you just confirm that that link is still in the chat and you guys can see it?
Yeah.
So of course, my God, start writing a report soon.
I can
I just started writing.
I can resend it. I'm not sure if you can see it if I sent it earlier. But so that that Google Drive link I sent has the slideshow presentation, the PNID, and the presentation order on it.
All right, I got it. Thanks.
Cool.
Yeah, when you get some multiple plasma. Yeah, but it really cool afterwards.
It's
I just need to add all these stuff.
I have my
You can't take that.
Alexa, Scott did get back to you, right? Okay.
It's like another 4 different countries.
Aha, got it.
I'm birthday. Oh. Do you feel like you guys have enough to officially do your like assignments?
I need to do that. I think. Or the temping ratios like.
Yeah, so there's a peak.
Yes.
Okay, that makes more
What were you thinking about?
I thought this was
No, just structures.
Yeah.
Structures.
Yeah, sheer moment direction. Like that's offense. I mean, yeah, either way.
This one looks kind of like.
It's a party that you didn't include this.
Okay.
Yeah.
I was thinking of it.
Didn't you just have my face?
What's up, Sarah?
Yeah, I did.
Why did I so?
Hello.
Why doesn't it have the peak then?
Like you know.
How's it been going so far for y'all?
Pretty good.
Good.
I mean, we made it here, so.
That's step one.
Yep.
That's what we had our.
Brian, I don't want to present you.
I don't want to present. It's a little too late for that.
Which is not like the
How much would I have to pay you to do the entire EDR and like Professor, what's his name? And I saw an accent.
Hey Scott, how are you?
Yeah. Or just
Turn your phones off or.
These can just have the mouse thing.
I need the guy.
When you were like starting.
Like in 10 seconds. I think we got everybody that said they were coming, so we can get started.
It's okay. I mean, not okay, like, but I didn't know, the reason I asked that, because I had, I'm not good to go out there. I don't know if that's gonna really happen, if you're gonna do the whole lab.
All right, we're gonna get started. Hi everyone, thank you for coming. Today we are here to show off our preliminary design for the propulsion system of Hybrid's next rocket, Spectre. My name is Brian, I'm the chief engineer of the team, and we'll get right into it. So Spectre's project goals entail a rocket that we plan to fly to 25,000 feet at the Friends of Amateur Rocketry launch site. We plan to fly a low altitude test launch at the Purdue Dairy Farm sometime before the FAR launch. And we would also like to develop a hardware catalog that we can use for future projects for the team. So our propulsion system requirements, the engine is going to bring the rocket to at least 25,000 feet. We are shooting for between a 25,000 and 30,000 foot apogee. The engine is going to deliver no greater than 9,200 pound-seconds in order to comply with the FAA Class 2 rocket impulse limits. We are going to have a thrust-to-weight ratio of 10:1 upon takeoff, and the engine is going to be the engine and its GSC is going to be capable of nominal safe operation at Zucro, Purdue Dairy Farm, and the FAR launch site. And getting into the overview of the rocket. So we've developed an O-class blowdown hybrid rocket engine that is using nitrous oxide and HTPB. We are supercharging our feed system to 1,000 PSI using helium. We are estimated to have a 2,100 pound takeoff thrust with a 550 startup chamber pressure. The rocket is an 8-inch outer diameter with a 6-inch combustion chamber. Any questions about our requirements or system overview?
Shrunk from the last time we talked, right?
Total
impulse.
The total impulse shrunk, yes. Okay. Yeah, so we after talking with you, we decided that we wanted to stick below the class 3. So yeah. So getting into our system simulation, we are predicted to have a 161 pound wet mass and a 116 pound dry mass to an apogee of 25,000 feet. The rocket is about 15 feet long in the current configuration. What we did for the simulation was we have a MATLAB propulsion simulation that we imported the thrust curve that we generated in that propulsion simulation into OpenRocket and input the dry and wet masses. And this is how we've run our OpenRocket. Getting into our propulsion performance simulation.
Hey, Brian, quick question for you.
Yep.
Sorry, can you go back to the previous slide?
Yep.
Okay. Maybe you'll get to this later. I might be jumping the gun a bit, but this type of simulation where we're looking at a Mach number of 1.4 goes a little bit beyond what OpenRocket is really built to simulate. So I don't know if you've done the other kind of flight analysis or maybe we're getting there, but I don't know how these numbers are going to look in real life just because OpenRocket, as last time I used OpenRocket, one of the things in the documentation is that it really struggles with trajectories that exceed Mach 1. So that might be something to look into.
Yeah, we've definitely seen some inaccuracies, we think, with OpenRocket when comparing the size of this vehicle to other teams' vehicles. So this vehicle closely matches Spaceport America 30K hybrid sizes. So we think that this rocket should be capable of going to at least 30,000 feet. So we have actually struggled to kind of get the OpenRocket to perform similar to those vehicle classes, which is why we think that this OpenRocket is going to be slightly inaccurate. But we did use it just to drive our preliminary design. We're working on integrating a flight simulation with our propulsion simulations so that we can get a more accurate apogee estimate, if that answers your question.
Yeah, I think that answers for now. Thanks.
Okay. Any other questions about simulation, flight simulation?
How I know it's kind of hard to model an OpenRocket, but how close does your CP and CG get during the flight?
They go, I forget what the minimum caliber distance is, but the 1.27 is close to the minimum from what I remember looking at. We get around a 2 when we go around Mach 1, and the 1.27 is about the minimum.
Okay. I would keep in mind that that open rocket assumes that motor is burning equal mass all over itself. When
Right.
in reality, most of your mass is coming from the top end. So I'm just gonna imagine that center of gravity is gonna move. I guess it's gonna move forward. Just keep that in mind. I think it's gonna be a little closer than what it is now.
Right. Okay, yeah, we'll definitely take a look at that. So some of our propulsion simulations. So we are starting with a takeoff thrust of 2,100 pounds with an average thrust of about 1850. We're looking at a 4.5-second burn time. Our chamber pressure is an average of 488, and our tank MEOP is 1,000 psi with an average of 805 psi. We have some other simulation outputs from our propulsion simulation, our mass flow rates. So we're starting with an oxidizer mass flow rate of 8.5 pounds a second, and a fuel mass flow rate of about 1.5 pounds per second. And we also have some other performance features, so our oxidizer to fuel ratio versus time and specific impulse versus time. We will get into later when we talk about our fuel grain geometry, how we've decided on this OF curve. But if you would like to look at these as references, they are here in the slideshow, and I can always go back to them. Okay, so getting into actual hardware, we are going to start off talking about our combustion chamber. So our combustion chamber, towards the forward end, we have our forward closure that mounts the injector. The igniter sits towards the top end of the combustion chamber. We have our HTPB fuel grain and our nozzle, along with our nozzle carrier. We'll get into the separate components of the assembly. This is just a top level overview. Does anyone have questions about like the top level assembly before we get into individual components? Okay. Great.
So I'm safe. I'm the engineer responsible for the injector. So this is our injector. It's a cavitating Venturi style injector. So essentially it's a shower head injector, but the holes are cavitating Venturis. And the requirements for this is that it must be able to choke the flow of oxidizer at a range of operating conditions. And also it must be able to achieve an oxidizer mass flow rate of 8.4 pounds per second, which is a propulsion requirement. You can see some of the specifications, and on the coming slide will show the geometry of the orifices in greater depth. So this is what each orifice looks like. So there are essentially two sections. There's the inlet and the diffuser. There's also the throat. So the idea behind this is that at the throat, the pressure drops to 55% of the nitrous vapor pressure, which we've determined is sufficient to cause cavitation, and in doing so, choke the flow and reduce feed-coupled combustion instabilities. So the diffuser half angle, which seems like an arbitrary number, it's 0.6 degrees, but that's actually the diffuser half angle of a specific bit we found on McMaster. So we're going to purchase a tapered drill bit and drill to a specific depth in order to manufacture this. And to the right, you can see some CFD we performed to validate the performance. So the color variation at the throat is indicative of an area of negative pressure, which is what we would expect from our sizing. We expect the pressure at the throat to be much lower than the chamber pressure. Questions? This is the forward closure. So what this does is it lies at the bottom of the combustion chamber, right below the feed system, and it essentially mounts the injector plate from below. So this is a bottom view. You can sort of see the bolt holes that are going to mount the injector. From above, you can see the inlet that lies directly below the intertank plumbing or the feed system. And on the sides, you see these counterboard holes which connect to the combustion chamber, the top part of the combustion chamber. It also contains O-ring seals. So these grooves on the sides seal against the combustion chamber. And you can look at the bottom view as well and see the face seal that seals against the injector plate. There are also two ports for pressure transducers. So there is a pre-injector pressure transducer. That's what that is. And then there is also a combustion chamber pressure transducer port on the side there. And you also see a table with specifications.
You guys thought about how you're going to tighten your pre-injector pressure port?
Yeah, so we understand that there might be a packaging issue with that port. We would either extend that once we've selected what pressure transducer we're gonna use, or put a fitting stack up there.
How would you do it without a fitting stack?
How would we do it without?
Yeah.
I don't think you would do it without a fitting stack.
So if you're gonna put a straight thread in there, right? Getting it wrenched down there, it's gonna be pretty cumbersome. I think.
Right.
Yes, I'll proceed if there are no questions.
Can you hear me safe?
Yeah.
You're only using that nitrous injector PT for test, right?
Yes, we will purchase I think it's called a plug or
Yeah,
yeah,
you'll
it's a
plug
standard
it for
part.
flight.
Yeah, we plug it for flight.
Okay, so even if you had to run a flex line or tube off of there, you could.
Any other questions? I guess I'll proceed.
So
Back one more, I'm sorry.
yeah,
And the same for the other port on top of there. I don't think you have enough meat on that. On that port.
oh, you're talking about this distance here?
Yeah.
Yeah, okay, we'll take a look at that. Yeah, you're probably right.
When you're catting it, make sure you include the hex. Because
Yes.
you don't include the hex and it gets the settle, it's a pain in the ass, asking if I don't have. You need to shave it off, so just make sure you're catting, or just take it into account.
Okay, sounds good. So getting into our fuel grain geometry, so we are going to be using a 5-petal flower geometry. The purpose of doing this is that is to boost our fuel mass flow rates towards the beginning of the burn by increasing the internal surface area of the fuel grain. And I'll show this on the next slide, but what from the analysis that we've done is that these this geometry of fuel grain is going to lower our OF ratio towards the optimum OF for the same length that a cylinder would at a longer length. The current geometry is 21.3 inches long, and we're predicting to have about 6 millimeters of fuel left after our liquid phase nitrous burn ends. This is to protect the rest of the liner and the wall of the combustion chamber and kind of help with our thermal management. This is some of the analysis that I mentioned going into the port geometry comparisons. So these are two fuel grains with the same port area and the same length, but one of them is a cylinder fuel grain and the other is the star fuel grain I showed on the last slide. And here you can see our average OF ratio for the cylindrical fuel grain is a lot higher than the average OF of the flower grain. So we have chosen the flower grain in order to sync our OF ratios towards the beginning of the burn and have the average sit closer to our optimum mixture ratio.
Do you have a calculation of your port?
No, I don't have a for the port Mach number.
Port velocity?
No, I don't. I will make note of that.
How have you vetted this geometry against prior art? Your own prior art or others?
So Hybrid's past two vehicles, Havoc used a cylindrical paraffin grain, and Nostromo used a star grain similar to the flower grain similar to this one. The flower grain we saw decent performance compared to the cylindrical grain. It was hard to do because of the limited hot fire testing we did on Nostromo. It was hard to directly compare how the geometry was affecting the mixture ratios. But we saw pretty stable burning in both the flower and the cylindrical ports.
Okay, now the shape of the field grain makes sense.
Mhm.
I'm talking about your thrust versus your port flow area.
Yes, the thrust variation that we saw
Not
on
variation.
like
Getting over 2,000 pounds of thrust in this diameter of a hybrid.
Mhm.
Has anyone else done that?
I would have to take a look, but yes, our mass flux through the port is higher compared to a lot of lab scale tests that we've seen. So that is one concern that we have with the current system, is that we are afraid that the oxidizer flux through the port might be a concern, just because it's a higher flux rate than most lab scale hybrids.
Okay, what other scales have you got?
Mostly we've seen between 30 grams per centimeter squared and 50 grams per centimeter squared for nitrous hybrids. We are operating around 60 grams per centimeter squared for our flow rate.
You're at 60 on nitrous.
Correct.
Did any of the papers go that high?
I haven't found a specific paper that's gone that high.
You have to watch for combustion instabilities,
Right.
and you might blow out the flame. It's outside my pay grade, but Cal was very afraid of going that high.
Okay.
So just keeping my eye on it.
Okay, we'll take a look at it.
It's also worth mentioning that like as you go higher in port mass flux, I don't know like what you guys are doing to like where you guys are pulling your regression rate, like your St. Robert's law or whatever
Right.
regression law parameters you guys are pulling. But you have to make sure you're pulling from a paper or some resource that created that like curve fit with port mass flux is similar to what you guys are running, because that can change pretty drastically.
Right. I would have to double check what the mass flux regions we pulled our empirical model from. But yeah, that's something that I will double check.
Also, your regression model is not using like edge blurring for the regression, right? You're just using straight idealized regression.
Yeah, it's idealized regression, which is just a function of mass flux through the port.
Yeah. So I don't know if that assumption holds as well as you get into the higher flux. I've never looked at it.
Okay.
Or if you're gonna have weirder edge burning.
Oh, okay. Any other questions about field grain geometry before we get into Jim?
Have you tried casting into this yet?
Sorry?
Have you tried casting into any of these geometries yet?
Yeah,
Did they do that with Stromo or?
Yes, yeah. So I helped out with the casting on Nostromo. And we have I'm going to talk about our field grain casting on the next slide too, or schooners.
We're saying here that too much stretch that size of the chamber.
It's likely too much oxidizer flow rate to actually burn in the port.
Gotcha.
Right, you're not gonna be able to ignite it, and if you do ignite it, you're gonna blow it out.
Okay. Yeah, we'll take a look at tuning the fluxes there.
You either redesign to go within prior art.
Mhm.
Right, folks that have demonstrated what's been possible. If you want to go to this higher condition, you're going to have to do some development testing to validate that you can do it.
Gotcha.
One of the reasons why I went so high on the trusts, because I gave them if you want to apply the dairy farm, you got to do 10 to 1 breast weight ratio. So we're not representing the stroke. So I think that's what they're trying to do is get that high on the breast. So if you guys have to go below that, right, that we don't want super low breast weight ratios.
Right.
Okay.
Right.
So,
Yeah, we'll definitely take a look at redesigning what that.
8%, whatever. That's
Yep.
fine. Just not 30.
Okay. That's it.
Yeah.
I believe the NASA Peregrine hybrid rocket went up to 65 grams per centimeters squared per second. I've also stumbled upon a paper that went all the way up to 130 grams per centimeter squared per second. They didn't have problems with flame blow up, rather they had problems with instability, but I believe they were able to reduce those instabilities with a sufficiently high pressure draw.
Is that for HPV?
I don't recall the specific paper that went up to 130 grams per centimeter squared per second. So I think it was something like HDPE. But yeah, I've seen
So that's high density polyethylene.
Yeah.
I believe the Peregrine rocket was paraffin, if I recall.
It was
correctly.
paraffin, yeah.
Yep.
I'm not referring to the peregrine was paraffin. I'm referring to
Right.
the other paper.
Okay, yeah.
Absurdly high. Yes.
Right.
At what chamber pressure?
I don't recall.
Because
Well-
obviously your chamber pressure plays into the velocity.
Right. Yeah, we'll take a look at. We're gonna collect some resources on that and take another look at it.
It's a fancy website I just made this weekend.
I took a look. It's a
I
great
just did it,
website.
right, and I found a couple papers that get pretty close to yours. on
Okay.
Facebook. So-
Okay, great. Awesome.
That must weight ratio, but I think I'll just stability. Like,
It's stability and, yeah, that's sort of stability. If you get really low, sometimes when it's windy or it's not balanced correctly, you get a little tilted. If you burn for 20 seconds, you go this way, this way, this way, and then you're.
You're always going to weathercock into the wind.
Yeah.
So it all is the relative velocity of the rocket to the wind.
I feel like there's like sims that like validate at lower thrust weight ratio.
They always do that. You guys don't have the control over what you're doing.
Well, if you get the off of the rails velocity, like you don't have the, they give a longer launch rail, right?
Right.
That was.
The longer launch rail gives you more velocity,
Right.
more guided velocity,
Right, but you don't need that thrust to weight ratio.
as long as you have a much longer
Yeah.
rail. Yeah.
So get far, it's fine, because 30, 40 foot rails. So here we're limited to like 12 feet.
Right.
So.
Okay. We're gonna hop into a fuel grain casting scooter. Hi, I'm Schooner. I'm the engineer responsible for the fuel grain formalization and casting. So we went with an HVP fuel to do its ability to be simulated and also its ability to not melt in like conditions at FAR. So HVP HVP 45M is what we currently have stocked, and it's one of the higher density HVP's variations. And so we went with a MDI due to its ability to be due to its characterization to cure at room temperature. So you don't need to, it doesn't require an oven to be baked. And then for the actual fuel to binder ratio, we went with, we did calculations based on the effective weight of the OH molecules to the NCO molecules in the binder. And so we came up with a 4.9 ratio of fuel to binder. And then for the actual, we decided to also add a little bit of additives, so we don't have radiative heat transfer from the burning surface to the internal parts of the grain, so we don't have melting before the flame actually reaches the HVP. For actual casting, we were just standard single long grain with a casting rod, and then end caps on each end to keep the casting rod concentric in the liner. And then to ensure that there's no adhesion to the core rod, we're going to wrap it with plastic wrap, which has been shown in solid fuels that also use HVP as a binder to reduce adhesion. And it's also made out of PVA, just in case we're unable to remove it, it's water soluble.
So the curative is not a a catalyst?
So MDI itself reacts with HEB and cures that at room temperature.
I would have okay. That's not an excessive amount of curative.
No, that's like what's recommended on like the manufacturer's website is usually.
Okay,
Yeah.
very good, thank you.
But it's been done before, yeah. Yeah, yes.
You're just sourcing this through RCS, I'm assuming.
Yeah, it's already sourced through RCS. That's yeah.
HBV 45M.
Yeah, that's like
PLO, whatever, and then MDI. What's the exact cured index on this? Because you've got the ratio, but what's your index when you ran your polyurethane calculations? Was it a
like
1-to-1?
Yeah, 1-to-1. So the hardness, if we're gonna do probably some initial testing to determine the hardness of the actual grain we want, so increase that ratio of like 1-to-1, 1.05 or something like that.
Yeah, because you're gonna deal with just a little bit of moisture, so I might bump that up.
Yeah.
Like,
okay. Yeah.
Take care of that moisture. You're doing this in a few months, correct?
I assume so.
Because MDI is a long sensitizer, so
yeah,
it's gotta be careful. So like development help you do that through long testing out there.
Yeah, I've worked with these chemicals before. Any other questions?
Can you hear me okay?
Yeah.
These percents, is this by mass or volume?
It's by mass.
Okay. How'd you arrive at 3% carbon black?
So that's just what's been used at previous spaceport teams, and that's been proven effective.
Cool. Are you gonna vacuum degas it?
Yeah. So before pouring it into the mold, vacuum degas, and then I'm not sure the facilities that we have, but I don't think we can vacuum degas while it's in the actual mold.
Depends on your batch size. So what's the dimension on this?
I believe the grain length was 21 inches, and then 3.75 inches, or sorry, 4 inches. Yeah.
Take some measurements and see if they want to vacuum up and down and seal and seal forward. What's your batch size that you're mixing? So
the actual mass.
Yeah, the mass of the HBV, MDI, and carbon fat.
I know the mass of HBV is about 7 pounds.
7 gallons.
Yeah.
It's about a gallon of it, so it's a lot. Be ready for that. The other thing, when you do it, you got to wear special cartridges in your mask so that it'll filter out these MDI compounds. I don't remember the exact ones, but make sure you double check with 3M. And then it's a pretty big grain. It's pretty long and it's pulling a lot of G's. You might want to do some surface prep to the inside of your phenolic to get better adhesion.
Okay.
We didn't have a ton of problem with it with Nostromo. It bonds pretty good, but the edges started to delam. We had to reinforce it, so just be aware.
You're gonna cast into, looks like a cardboard tube?
Cast tube, which seats into the phenolic.
This is a commercial purchasable thing?
Yeah,
always really rocket.
Yeah.
How are you making your manual?
3D printed PVA, and then so it's gonna be printed in segments and then like notched into each other.
Is there any structure at the center of that, like a dowel or something? It wasn't planned. I don't really see I don't see it being like caved in by the mass of the propellant. Okay, I was when you're doing.
Yeah.
Just making sure that they're all going to line up, one way or the other.
That would be a good idea to apply some structural integrity to it.
Are you going to print a little bit of a taper?
That wasn't planned. What would be the reason for the taper?
Make it removable.
It's water soluble, so it just.
Yeah, I don't think they're looking at
the mandrel's water soluble.
Yeah,
the mandrel's water soluble PVA, so then they don't have to worry about the angle.
Yeah.
Have to.
Okay, cool.
What I might say is instead of that plastic wrap, use electrical tape and just spin it around in a spiral pattern up, sticky side in, that's gonna stick that plastic wrap to it. And then you just fold the tape out.
Okay.
How do you get the-
I've
how do
used
you
plastic
get
wrap
tape into
before.
the-
For I've used plastic wrap for solids before, and that usually works extremely well.
One thing with putting pieces of the mold together, make sure it's straight and that it dries straight. And then depending on what you use to seal the layers together, sometimes that will bond to the HTPB. And then you end up sitting at a table trying to scrape out the glue in between the layers that stayed in.
Okay.
So use use something you can get out.
Any more questions?
I'm just curious.
Yeah.
How do you print the PVA?
Like 3D printer?
So it's a filament,
Yeah,
but it's water soluble.
Yeah.
Yes.
Probably printed in my apartment.
Probably printed in my apartment.
How tall of how many pieces we have to print it in?
My bed size is 11 cubes, so we would probably have to do 2 pieces for this. 2 or 3 pieces.
Are you printing it on a bed slinger or is everything moving the bed back and forth or?
Yeah, we also have the Potter facilities now, the PSP's like new printers in there, so we can print in there as well. So
Yeah, I would do it on a stationary bed. If you can't get access to one, let me know.
okay. Sounds good. I think that's it. Miles.
Are you going to try to use force to push it out, or are you just gonna use water?
I think we're gonna use water, and then that's the plastic wrap would be for if is there anything that's not coming out or not dissolving, then it would be, that's how it would be removed. It would be able to slip through the plastic wrap.
So are you gonna discard the cardboard tube?
No, it'll be cast into the cardboard tube and it'll sit in the combustion chamber.
Right, so how do you protect the cardboard tube when you're using all this water to get the liner out, or the mandrel out?
It's a good question.
Yeah, so Brian, when we did this, the phenolic itself protected the liner because it was phenolic's pretty waterproof. Your normal cardboard won't have that effect. It'll dissolve.
Right.
So
Yeah, we'll have to reconsider that then.
Is there a reason you can't print in the phenolic?
Yeah, it has to do with the fit of the aft phenolic for the post combustion chamber. The phenolic helps the fit be a little more snug. We sourced the post combustion chamber phenolic from the old hybrids, from the 6 hybrids. And the Always Ready Rocket 3 commercial one we bought is the outer phenolic. So in between those, it's the casting tube helps fill that gap in. The 2 current size phenolics.
To clarify, it's the phenolic from Always Ready Rocket, not the blue suit, correct?
Yes,
Okay, I should make sure.
Okay, I don't understand the stack of wood for the.
There will be a slide later. Yeah, it's labeled.
Miles. So for our nozzle carrier, or for our nozzle, the machining limitations we needed another system in place to keep the nozzle within our combustion chamber. So we have a nozzle carrier. It's made out of aluminum, 6061T6. It's connected to our casing via bolts, which are threaded into the nozzle carrier and then flush with the outer casing, so pinning it to the casing. It is we're using a double ring seal between the nozzle carrier and the casing, and then RTV silicone sealant between the nozzle carrier and phenolic liners. And then the nozzle simply rests on top of the lip inside the nozzle carrier. We also did FEA to ensure that the force of the pressure within the combustion chamber wouldn't be an issue. And we got a maximum stress of 7,411 psi. Yeah, the slide with closer up views here. Are there any questions?
There's not gonna be improved in the graphite, the clearance, those fasteners, right?
Correct, yeah, those fasteners will be shorter, they just clip into the assembly and.
I would really double check this. Flush as you can get, because I can just imagine somebody taking one of these things and being, nah, it's not going in, and just cranking and cracking the phenolic.
Yeah.
What are you making the nozzle from?
Graphite, I believe it's the ISO 2020.
Super fine assembled. Say where we're making the graphite?
I asked what it's made from, and
Oh.
yeah, where are you gonna machine it?
Caleb's gonna actually, one of our alumni are gonna machine it, Caleb, he has a lathe back home that he's going to machine it for us.
If you guys crack it with those bolts, I'm gonna be really sad.
This is the stack of tricky one, you can see, Scott, where the, that yellow, this yellow is our full length, phenolic. The brown there is the casting tube, and then the orange is the post-combustion chamber, or post-combustion chamber liner. So to make that fit work, we decided to include the, casting tube. The casting tube came with the Always Ready rocketry, phenolic. We didn't plan on originally using it, but then when we discovered the fit issue, it was just a perfect fit, so that's why we decided to use it.
And which piece is the liners from the 2015 hybrid?
That's the
Which
orange
color
piece. The orange piece, yeah, so that, you can't see the ear, but that ends below just below the fuel grain.
They're using my 2015, 415.
Yeah, just to make your at the combustion, post-combustion length, right? That's what you're talking about.
Yeah.
Yeah.
So there's actually a quick comment on your stack up. You've got the fuel grain cast into the cardboard tube, and then you've got another phenolic nestled inside it, and then you've got a main phenolic on the outside of all of it. But if you compromise that cardboard liner that the fuel grain's cast into, there's nothing holding your fuel grain actually anymore. So what's to stop it from sliding down into the nozzle?
Right, but it also sits on top of and I'll pull up the, just for clarity, I'll pull up the.
On top of the other phenolic, the nestled piece, but that's gonna be right in the hottest region in your nozzle.
Right, but yeah, you are right, if that, if that casting tube gets compromised, then yes, you're gonna risk the stability of the fuel grain inside of the combustion chamber.
It would be better to cast your fuel grain directly into the primary phenolic and then nest those other pieces up into it somehow afterwards.
Right, yeah, I think that's what we will do for that.
Yeah, we could just make the casting tube not full length, just make it the same length as the post and pre.
Right, and we'll cast the fuel grain to a larger diameter.
Yeah, appreciate the comment.
So you'll use the cardboard just in the post.
And pre,
Right.
yeah,
Yep.
we can do that. That makes sense.
Jim, did you have a question?
Okay.
Okay, cool.
Could you go to that? That slide is perfect right there.
Okay.
Correct me if I'm wrong, but I believe that there's a leak path between the graphite nozzle, and then through the 3/8 inch bolt, right?
Oh,
because
sure.
you know what I mean?
This, can you see my mouse? Is this?
Yeah.
Okay.
Yep.
So we plan to have RTV silicone here in the carrier and on the liner. This is to act as the sealant. So this there wouldn't, well, if this region where my mouse is doesn't act as a leak path, then this shouldn't, is the idea.
I got you.
Why are you gluing it to the phenolic? You're gonna glue the nozzle to the phenolic?
Or sorry, the RTV will be on the carrier, not the phenolic.
Okay, the carrier assembly.
Are you worried about pressurizing the phenolic, Caleb?
Just the phenolics. It's card. I'm worried it'll flex, and the RTV won't hold up to that. And then you would also make your assembly non-disassemblable, and
Right.
you would create a unified assembly of the two, which you really don't want for practicality's sake.
Right. That makes
The,
sense.
the RTV has worked in the past. Make sure you clamp the pieces together positively and they're a good fit, because the pressure area can't be very large or it'll blow out. You also have room to package an O-ring on the straight region of the nozzle. You don't have to, but it might be a good redundancy.
Gotcha. Yeah, one of the we were curious about the machinability of an O-ring groove there. But the
In your carrier?
either in the carrier or machining the groove into the nozzle.
Yeah, don't put the stress concentration in the nozzle, but there's no reason you couldn't put one in that carrier.
Okay. Okay, yeah, we'll take a look at that then. Any other questions about the carrier?
This is your own design for the carrier?
Correct. And yeah, there's the assembly. And an overview of our nozzle. We're making the nozzle out of ISO 2020 graphite. Like I said, machined by Caleb. Thank you, Caleb. We're sitting at a 5.21 expansion ratio with an optimized ambient pressure of 14.7 psi. So we're going to be operating perfectly expanded upon launch. So we're going to go into our igniter if there's no more questions about the nozzle or the nozzle carrier assembly.
All right, hello everybody. My name is Simon. I'm one of the co-leads for the propulsion team, and I'll be presenting the igniter. So the igniter consists of two parts. We have a solid propellant core, and then a paraffin wax outer ring around that that'll bridge between the solid core and the inner diameter of the phenolic in the combustion chamber. We'll also add a little bit of magnesium shavings into that paraffin wax outer ring just for a little bit of additional thermal energy for the ignition. We'll use an E-match pyrogen to actually trigger the igniter. Our plan for that solid propellant core is to use the Purdue propellant formulation, casting in coordination with the Spaceport PSP team. If that falls through, we're also looking into partnering with somebody who has an L3 rocketry license, and we will consider using a commercial grain as well for that. This is essentially the same design that was used in the past on the team for the Nostromo launch, scaled up slightly to accommodate the larger motor size. It has around 1.5 times the solid propellant mass as the Nostromo igniter did.
Which rocket was the Nostromo?
It's the senior design rocket.
Okay, it tested last spring.
Yes, that flew in April.
We started testing the spring, like January, February, and launched in April.
Okay.
And we saw great success with the igniter, and so we don't see a reason to use an alternative. Any other concerns?
If your peers are holding you up for the grain casting and the license for the grains, we'll just buy you a grain, cut slivers out of it.
Okay, thank you. All right.
Yeah, that seems reasonable. Your mass flux is a lot higher, so just be aware.
Yeah.
If it blows out, do something different.
Yep, we'll definitely adjust during testing if that's necessary.
Right.
I'll now discuss the flight tank that we're planning to use. You can see kind of some of our top level parameters there. We're looking at around 2,100 cubic inches of volume. We have a maximum allowable working pressure of 1,200 psi, planning to hydrostatic to 1.5, which is 1,800 psi. The system was built with a safety factor of 2.0, which brings us in line with the Spaceport America Cup design guidelines. The entire system will be constructed out of aluminum. It has an 8-inch OD. Primary wall thickness along the length of it is 1/4 inch. It's around 55 inches long and weighs a little over 40 pounds. We're planning to have a 1-inch SAE ORB port on each of the head caps, and then on the aft head cap, we'll also have 2 auxiliary 1/4 inch SAE ORB ports. that we're planning to use for instrumentation. Primarily, we'll add a thermocouple there to make sure that we're getting temperature of the liquid phase of the nitrous oxide. Also integrated into the head caps are Radax coupler joints, which we'll discuss a little bit later on in the presentation. And then the head caps will be secured with a bolted closure, and then we have O-rings for the seal. Discuss a little bit more of that in detail. So you can see
The factor of safety of 2, is that on yield or ultimate?
that is on yield. And I'll discuss where that is derived as well. Here's the design of the tank head itself. It's bolted with an O-ring seal, as I said. We're planning to use 2 redundant -365 90A durometer nitrile O-rings. We'll run contoured backup rings on those just for a little bit of extra support. We're going to use 23/8-24 button head screws. Those are arranged in 2 rows of 10. And then the actual head geometry is torus spherical. Our goal with the particular geometry was we were trying to minimize weight and length to reduce the amount of stock that was required to machine it from. FEA analysis of this shows a safety factor of 2.09 on the head with the auxiliary ports. On the head without ports, so the forward head, it's a little bit higher. And then the structural analysis for the bolts and wall stresses are seen here. So our primary failure mode on this will be tear out of the bolts on the head caps there. You can also see the stresses in the primary wall of that tube. The lowest being our hoop stress at 2.15 on our factor of safety.
Would you go back and show the It's 24. So it's just a through hole so a close tolerance through hole for
the outer tube, and then we'll tap the head itself to secure those bolts. And we chose the fine thread just because they'll give us a little bit more strength in the shear direction, the shear loading.
How many diameters are your tapped holes?
I believe currently they are spaced 0.6 inches from center to the edge. And that was selected, so that's a little below 1.5, I believe, off the top of my head. And that was selected to bring our factor of safety and tear out a little bit below the failure and hoop on that tank.
how it's a 3/8 diameter fastener.
Yes, that is
How
correct.
deep is the threaded portion?
1/4 inch.
So typical design for aluminum is like 1.5 diameters depth of threads. That's usually for primary tensile loads. So you might get away with less, but
Yes, that was something we considered. The belief was that because we're not loading that joint in tension, only in shear, that the depth of the thread was less important. But we can revisit that if you believe that's going to be an issue for us.
that's up for you guys
It
to
needs
find
to
out.
be- Essentially, your bolt is cantilevered from the threaded hole,
Yes,
right?
that's correct.
So if it's not threaded deep enough to where there's slop in that cantilever, right?
Yes, I
then all
understand.
of your stress analysis is bogus, right?
Correct.
Because you're now putting your aluminum part in bending in a moment on that hole instead of it being loaded in shear.
Yeah, we'll look into that, increasing the depth of the head there.
Well, what I'm wondering is, you don't have a limitation necessarily on the thickness of your head where these fasteners go in.
We do not.
Did you look at shoulder bolts?
With a unthreaded shank, is that what you're referring to?
Yes, so you're actually pinning the parts together with the threaded part just to keep the pin from falling out?
I did look into that. I was unable to find a vendor that would supply them in the appropriate geometries or the correct size, if I'm understanding what you're referring to.
Master?
Yes.
Then from what you could choose, what was the constraint that wouldn't fit a design that you could come up with?
The problem with so just to make sure we're on the same page, when you say describe the shoulder bolt to me, I just want to make sure.
Drawn on the whiteboard.
So my understanding of what you're referring to is like that, and then we have an unthreaded portion, and then so it's partially threaded. Is that...
No.
Okay.
Erase your threaded part. Just make the bolt a little bit longer. Okay. Square it off. Now make the threaded part smaller in diameter than.
Okay, I understand. Like that.
That's your threaded part.
Okay.
So you can do a very close tolerance hole in both parts so that they're pinned together.
Yes.
And then the threaded part on the end. So it would require, I mean, you could do quarter inch.
Yep.
But then in the band where you have to put in the threaded parts, you have to thicken it a bit.
Yeah. We'll for sure look into that. That seems like a good.
It might work to give you accomplish the intent of your design.
Yes. We'll for sure look into that. I appreciate that suggestion. Are there any other questions about the ox tank design?
Somebody's writing all these down, right?
Yes.
Somebody taking notes.
Yes, we have a couple of note takers.
There's another comment back to me before. Just keep in mind how you're gonna pinch that in there, tighten that. That fork.
Oh, yes. That's a good point as well. We'll look at that.
Socket.
What are the angled holes for? Is that an airframe thing?
That is for the coupler design, which we'll discuss in detail later on.
Okay.
Yeah, so it couples to the airframe. Right. And then the forward tank instrumentation manifold schooner, you'll start us off with that.
So the design requirements for the forward tank instrument manifold were to withstand the pressures of the flight tank, as well as allow 2 relief valves and 2 pieces of instrumentation access to the pressure within the tank during flight and during filling. So we decided to go with a hexagonal shape to fit within the 8-inch diameter profile, while also allowing our valves and instruments to be offset by 120 degrees to make it easier to basically wrench these parts in to our during assembly. The actual ports for the instruments and the relief valves are 1/4-inch NPT holes. They're on the side and on the top. The top hole is basically for the thermocouple to go directly into the tank and measure the temperature of the ullage of the nitrous oxide. The bottom port is an SAE ORB to match the same port as that is on the upper forward closure of the tank. And then the failure mode for this piece of hardware is the tear of the threads of the actual threads on the ports. Any questions?
So how is that attached to the?
So there's a fitting between the lower port and then the upper tank that is going to be attached.
Male.
Yeah.
I see.
Okay, so the part we can't see there has a female straight thread port.
Yes, it's a SAEORB. That's right. For the actual relief valves, we went with a burst disc, with the disc having a burst pressure of 1650 psi. This is due to the actual tolerancing due to manufacturing of the burst disc. So this is a little bit higher than what we actually wanted to burst at, but due to 6%, 3%, we decided to go a little bit hydrostatic test
to a higher pressure, so we ensure that all the other hardware can withstand the pressures that the burst disc is rated to. The safety head is sourced from HIP, a industry standard, and then for the relief valve, we went with the Peter Paul series. It works within the operating pressures that we're going to see, and also is nitrile for the O-ring, so it's mostly nitrous compatible. If I know earlier there were issues with temperature. The operating temperature of this valve is 0 degrees to 140 degrees Fahrenheit.
It's a potentially pretty stupid question.
Yeah.
That's 45-degree layer out of 37. High pressure.
Yeah, so high pressure equipment make going into autoclave style connections.
Mhm.
So what you're showing there isn't a NPT, but that may just be.
It's just the CAD that they had. That's what they gave us. Yeah.
So you verified you're.
Yeah,
what
yeah.
you can get will have a mail.
Yeah. Yeah.
NPT. What are you making the part that you had just up there a second ago out of?
Aluminum 6061.
Do you care the clocking angle of these three things relative to the tank? Relative to the rocket?
They're not oriented. Like they don't require a certain orientation to.
They don't have to hit holes in the airframe.
Oh, yeah, they do. Yeah, for actual like assembly, yeah. But the piping can be so these are going to be adjusted to be 90 degrees, hopefully.
There's a couple solutions to that. So one, you'll see from our coupler slide later that we plan on putting the pins between the airframe and the coupler in after installation, so we can test the orientation of this relative to the airframe before we put the pins in it. That will lock the airframe from not being lockable. Also, there are lockable SAE fittings that are sold. They're a little more expensive, but we can also look into buying those. So the actual whole manifold could change the issue.
So once your plan is to thread all that stuff into that manifold and then thread the manifold into the tank.
I believe it would be manifold first and then, or yes, yeah. Sorry, yes.
For that Peter Paul, you can't get it in once the manifold's on.
Yeah.
So are you able to get a wrench on that somehow? Or how are you gonna tighten it?
It would, sorry, I misspoke. It would be put it on the manifold first and then into the tank.
Okay, make sure that Peter Paul is one big piece, that solenoid valve.
Yeah.
You're probably not gonna be able to put it on once the manifold's in place.
Okay.
I only mentioned this because it was an ongoing problem with the last one, and we ended up using a flex line.
Okay.
So the picture you're showing here is fully assembled, and then you screw that onto the top of the tank closeout.
Yeah.
Okay.
So you could just put wrench flats on it.
If you use an adjustable fitting for clocking, you're gonna have to get a wrench in there to tighten the jam nut that seals it.
Mm-hmm. Well, so if I'm not mistaken, there's no airframe around it, right? It's just open space, so you can open. You can.
But it's down inside the top of your tank closeout.
Yeah.
Well, if you have the stem.
We'll look into the access of that.
Yeah.
I'm not sure if we could probably look at it through CAD. If I can port maybe like a wrench in the CAD. One thing we can look into is raising the actual head of the port on the aux head, just so it's flush and we can access it.
Look, print it too. Print the assembly out and actually pretend to do it.
Yeah, that's a good point as well.
Cool.
Thank you.
I do have one comment. Is there any reason it's aluminum 6061 versus any other aluminum type?
No, it could be other. This was done for.
Or B7055, which is just wrong.
Okay.
There's free stock in Bachelor and the 755, so we might use that instead.
Also, I don't know how useful this would be, but we could, in theory, water jet our own wrenches our own wrench shapes if it ends up being to put a normal wrench in there. I've seen other teams do it.
No.
Interesting geometry.
No, custom tools are a bad solution to an engineering packaging problem. Because then you'll get to the California and it won't have it. You'll be sad.
It's also always interesting to screw stainless steel NPT fittings into aluminum.
Yeah.
Right, you get to do that once.
Yeah.
That was one reason we decided to create a separate manifold rather than multi-porting our box tank head, because we ruin that part, it's gonna be a lot cheaper to replace. But yeah, ideally we'll have to just practice on that.
Well, if you do, you can always use straight thread O-ring fittings.
That is elbow.
You can make and break those as many times as you want. It's the NPT with the tapered threads.
Okay.
You're essentially gonna be machining your aluminum with the stainless fitting every time.
Okay.
Yeah, any other questions?
Okay.
So then one of the considerations we have on the actual flight vehicle, so this is all flight hardware, this will not be used during any of our hot fire testing, is we want to ensure that the vent valve is selected to be normally open, so that if there's any sort of power event or failure of our ground systems equipment, will automatically vent the tank so that the vehicle will become safe. But during the course of the launch, there's a short period of time where the electrical disconnects will have fired and the vehicle will be moving upward through the course of the burn. And during that time, we still want to ensure that vent valve remains closed, just so we're not losing any tank pressure and performance in that event. So we've developed some custom electronics that will help to keep the vent valve closed just for the short duration of the burn. So you can see kind of the designs pictured there. It's been developed so that we have full control with the GSE before the launch occurs, so there will be no sort of delay in controlling the vent valve. And then only when the electrical disconnect on the rocket actuates, there will be adjustable through a variable resistor time delay that will keep the vent valve powered for a set period of time before it'll shut off and the vent valve will open again, just so that we're always there will be no situation in which the vent valve is stuck closed. And then to provide power to the vent valve during that short period of time, we'll have 3 14500 commercial lithium ion batteries. We estimate those will weigh about a quarter pound. So not a very significant weight. And then the design has been validated using LT Spice simulations.
All right, I'm going to jump in for a minute because I see electronics and I can't not comment. So this board looks pretty promising. I think given you've already done some LT Spice, so it sounds like you're ahead of the curve. One thing you might want to consider for like wiring harness type fixtures, Molex connectors, like the connectors you have there pictured, they're fine. But you want something that's going to handle vibration and temperature and any kind of crazy stuff you throw at it. So it might be a good idea to stick with something really basic like screw terminals.
Okay.
A lot of the off-the-shelf boards use entirely just screw terminals, and we haven't had any problem with it. I think this would probably work, but for future purposes, that's probably something you want to lean into. And then the second thing I had is I worked on a previous iteration of this board many years ago, and we never really got it to do what we needed it to do. But since then, I've realized that I believe it's Texas Instruments actually sells an off-the-shelf the commercial integrated circuit that does some of the power switching logic internally. It's the same IC that's used in like laptops for switching power between a charger and an internal battery. And that's something that may or may not be useful, but I'll attach the data sheet in the chat.
Yes, I would appreciate that. I'm not going to profess to be an expert at electronics, so I appreciate
okay, neither am I, but I'm here anyway.
Yeah, so those connectors were chosen. Those are JST XH connectors, if I recall correctly. One of the advantages, the reasons I went with those over just the screw terminals, which I did look at, is these will be a little bit easier to kind of plug and unplug as we're adjusting the systems. But I'll definitely look into the sort of vibrational loading, and if that does prove to be a concern with the connectors I've selected, we'll switch to screw terminals.
Okay, and like I said, it's for your purpose, it would probably work either way. But for most rocket hardware, you're not going to see plug and play connectors. You're going to see screw terminals.
All right, I appreciate that feedback. Are there any other questions or comments on this? All right, move on.
Hello, everyone. My name is Alex. I'm the propulsion co-lead along with Simon and responsible for the intertank. So just some general things about the intertank. As you can see here, we're including hatch in the lower airframe piece in order to read the valve state while testing of our run valve. And then for our fitting stack up, we're mainly going to be using anodized aluminum fittings from a source that we have online to reduce weight and things like that. So we're going to start off with the run valve team. Do you guys want to come up? Yep.
Hi, I'm Theo.
And I'm Kiwano.
We are two of the members on the Run Valve Team New Member Project. Oh yeah. So we were tested to design a mechanically actuated onboard run valve. It needs to actuate in 300 milliseconds or less to fully open the valve in time. The valve needs to open about 90 degrees, or sorry, not about. The valve needs to open 90 degrees, and we're using a 2-to-1 gear ratio. So our servo needs to actuate 180 degrees in 300 milliseconds. We are planning, or we were discussing using a magnetic disconnect. We are now discussing maybe using mechanical disconnect instead. We are still figuring that out. They used a mechanical disconnect last year, I believe, which would probably work for our needs, but we need to do some more research on a better solution for that. And looking at servos online, we ran into an issue of trying to get enough torque, but also enough speed on our motor. So we have found a motor that meets our torque needs and is relatively close to our speed needs. So we are going to purchase it and do some testing with it and attempt to overvolt it to get faster actuation times. There is some, it depends on if the motor has a built-in microcontroller, because that can be damaged by overvolting. And we're not sure by the listings online. So we need to do some more looking once we actually get the part in our hands.
And about the ball valve, we found one online from a manufacturer called DiverChoice, and it's made out of stainless steel, and it's 2000 psi rated, measures compatible PATFE, and 0.98 inches diameter, and this is our whole assembly of our system, and all the colored parts are going to be manufactured, and the faceplate and the connecting plate and the valve shaft will be 3D printed. The valve casing we will manufacture out of a hexagon aluminum, and we will have extra holes on the valve casing so we could get a set screw to secure the valve in place.
Have you guys looked into how much battery you would need just to have that actuation?
We have, we're still trying to figure out how much power we need, but if we do need more power, we plan to hook up a 3S LiPo battery to provide the voltage we need. We're also discussing how our design is going to work with the DACs, get power to communicate with that. We might need to buy an additional microcontroller to help communicate with the servo. So
you do plan on putting on more battery for this? Is it correct?
I think we still need to do more research. I'm not sure yet.
In the past, offboard. In the past, we've used an offboard battery for it, and it's works. So discuss.
So Sherman had an offboard battery that used that. The battery, actual battery.
There was a LiPo battery that was integrated with the ground systems. Yes.
Yeah, and the valid question is like how many milliamp hours we actually need to actuate.
Right.
Because once you get in like those very, very low milliamp hour 3S ranges, it's pretty light. So it is a good question. We'll look into how many actuations. The only thing that sort of makes me nervous about that design is if we spend a lot of time on the pad that no, hours are reducing over time.
Actually, a magnetic one, is it possible to like have it like see power? Right?
That's the question.
A similar circuit to what we've developed for the vent valve.
Yeah, exactly. That's what I'm saying. Like, if you were to have the system vent valve, you can just copy and paste it down there.
Yes.
Yeah.
Or you could just make the ground power wire long enough that the valve has time to fully open before the valve has.
So the plume doesn't go away or it gets snagged or right? After.
So-
Yes.
Oh, I was just gonna say, we did a bunch of math about that on Nostromo. Well, a bunch of math, but your speed's a little bit slow, but it shouldn't move more than a few feet at a time.
Right.
We went away from magnetic disconnects because they had a habit of one, blowing off of the wind, and two, when that rocket starts to move, if you're counting on the wire to keep doing things, it needs to stay connected. You need a very good connection.
We have a slide. Yeah, we have a slide.
Yeah.
Yeah, your second thing is, how did you set your torque requirement for this valve?
So we calculated using the data from or from our previous rocket and yeah.
We have test data from previous rockets that use similar servos, so we've been using that to estimate our numbers.
Yeah, it's based on the Havoc offboard pneumatic torque fetted output that would wall out.
Okay, based from the Habenim data sheet.
Yes.
Okay. That will work. It's probably conservative.
Okay.
Just a thought, if your speed is an issue.
So operationally, during the last launch, I think the physical connector got pulled out of the rocket half a dozen times. Right, tripped over, kicked out. I think it pin broke at one point. So if you guys do go with the mechanical, separator,
Yeah.
like I would have it be super simple to plug in at the last second before you need, because it was just getting knocked out.
Yeah, we've just begun thinking about this. There's actually a slide on it a little later.
Well, perfect.
Yeah, we're planning using USB 3.0 connectors. So.
Yeah.
So about the time, if we overvolted to 8.8 volts, we were aiming to like get about 212 milliseconds. Is that too slow still?
You gotta look at how many G's you're pulling and do your acceleration, but that's also probably your unloaded speed, right?
Yes.
So I don't have a performance curve on that motor for what it does when it loads up, but it's probably a lot slower. And you need to get that valve open enough for sure that it doesn't become the choke point in your fluid system. Was always our big fear. That's rocket science, but.
Any more questions?
You guys have one of these in here?
No, we don't have any of our parts yet.
I know, I emphasize don't buy parts until CDR, right? But for things like that, it's $100.
Yeah.
We're
gonna test it.
right.
We're gonna test it.
I mean,
Yeah.
the expensive things.
Yeah.
Or machine things.
Okay, yes.
One thing, Chris, the
Yeah.
connector that kept coming undone was the upper one, and it was mainly because I forgot to glue it in.
Okay.
There was no access
Big
to it.
wire everywhere. I mean, taken it out a couple times.
Yeah, that one was awful, but the bottom one should be okay.
Good.
So what size is this valve?
The valve, it is.
Well, let me change the question.
Mhm.
What is the liquid nitrous tank outlet connection size?
It is a 1-inch SAE port.
So you plan on running 1-inch tubing,
Yes, that's correct.
and that's the connection to the inlet to the injector?
Yes.
Okay, so what size valve, or what's the CV requirement for the valve that goes between those two?
We plan on making our ID. We're aiming for 1-inch throughout the inner tank. So I think it's a 1-inch nominal, but it's got 0.98 inch IOP. It's got 1-inch NPTs on the side of it.
A 1-inch valve will have like a 1.3 inch, 1-inch tubing is like 1.3 inch OD. This may be a half-inch valve.
From the chart on their data sheet, it listed like nominal, it was like a nominal value and then an ID for it. It said 1 inch and 0.9 inch. I may be misremembering, but we'll definitely look into it. Make sure.
Do you have CAD for it?
No, we do not have the exact CAD,
Yeah, they emailed the vendor, and
but
all the.
So is the ID the ball ID or the connection size or
I'm pretty sure it's the ball,
the ball ID?
the ball ID.
Okay,
Yeah. Yes.
so it would be good to put on here, what, is it a 1 inch NPT valve, a 3/4 inch NPT valve, etc.
Mhm.
And then the valves are typically characterized by whether it's a standard port or a full port.
Are there ball valves out there with more friendly external geometry? I think.
I'm not sure. We
We did a lot of researches, but I think this was the best we could find and affordable we could find. So
I think the problem we're running into is that all the ball valves that had a good shape to be paired with a motor already had a motor attached to them that was much more expensive.
Mhm.
So we were trying to save some money by designing our own system.
Is high pressure systems sell ones that are NPT fittings? Not sure.
Yeah,
Okay.
not sure.
So
Yes.
I know you can just buy the high pressure systems, ball valves without the massive pneumatic actuator attachment, and those are pretty friendly to mount too.
Okay.
Yeah, but they're gonna weigh
Fair.
5 times what a low pressure, high pressure equipment valve is 10,000 PSI.
Yeah. Okay, good. So next thing we're gonna talk about is the quick disconnect. This is connected at a T just above the run line, just below the aux tank. It is a design that's been proven before at a smaller scale on Stromo. We currently own the 1/4 inch helium rated run line hose that will go into it. And it works basically just by using a McMaster stainless steel high pressure quick disconnect coupling and pulling that back while pushing itself off the rocket. It'll most likely be connected to the test stand / launch rail by some sort of system that will make it so it doesn't hit the ground. And those 2 orange actuators there you see we also currently own our 60mm stroke pneumatic cylinders. Any questions about this
Just a
system?
little piece of advice, if you look at the when we zoom in launch, that took 5 years to get that first rocket off.
Mhm.
And for 5 years, we all set out to figure out the quick disconnect when we get there. That's why there's 2 half pan of Nards buckets in this photo, right? I would put a freshman or someone that had a lot of time just to focus on how to carry that.
Okay.
It seems like it's a pretty simple thing, and it's usually rushed together at the end. It usually involves, stretchy cord and whatnot.
Yeah,
So,
exactly. Yeah.
Yeah.
So we'll plan that system out.
So the QD will have integral check valves.
Yes, it is. Yeah, check valve inside of it. The check valve, I believe, only operates once it's disconnected, so it doesn't act as a check valve while the 2 are connected. Yeah.
Are you doing the valves in both halves or just in the side that's on the rocket?
Which valves?
So if you've seen a shop air hose connection, right?
Yep.
Yeah.
The female's on against the wall.
Mhm.
The male part does not have a valve inside, it just goes straight through.
Right.
Right? It's up to you made them that the valve inside the female part allows flow.
Right.
You can buy quick disconnects that have the integral check valve in the male part instead of the female part. As well as in both.
Okay.
So be intentional in your design what you intend.
Got it. I believe the current McMaster part we have is just the female side, but our dump and fill valve should be closed by the time we disconnect, so it shouldn't vent all our GSE on the male side, if I'm understanding it correctly.
So if you've got an integral check valve in the QD, why do you need an actuated valve? Can you get rid of an actuated valve on the rocket?
No, there's no actuated valve for this, right?
No, no.
Just the run valve.
Yeah, the run valve is the only actuated valve inside the rocket.
Yes.
So it's the quick connect integral valve that prevents the
flow
nitrogen
outside.
from flowing out of the rocket.
Yes.
Okay.
Oh.
And is the male or female on the rocket?
The female's on the rocket.
Females on the rocket.
Yeah, I think yeah, the socket or the plug is on the rocket. I think McMaster they call them plugs and sockets. I'm not sure.
So a plug would be male, a socket would be female.
Yes. Oh, okay. So the male's on. Sorry, apologies. The male's on the rocket.
Okay, that makes sense.
Okay, there we go.
But it has to have the valve integral to it.
Okay. Yeah. And it's not shown here on the CAD, but there's two push to connect hoses that connect to the top of those orange lines that will come off a solenoid on GSC with 100 psi nitrogen. All right.
Quick thing on this.
Yep.
I would set your CAD so that when the cylinders are in the retracted position, they're not, either do it manually or design it where the cylinders bottom out, not the plastic part.
Sorry, the cylinders are
You
what?
see how your CAD has that blue and green part flushed together at bottom?
Yeah. Mm-hmm.
If you're gonna power it in both directions,
okay,
design it so that the cylinders bottom out and don't pull those little bolts through the plastic shoe.
Okay, that makes sense. So make it like a little gap there.
Air gap it, yeah.
Cool. All right. As opposed to that very proven system, this is more of a novel system. This is our feed system interface. So this is what connects below the run valve into the top of the upper closure, forward closure of the combustion chamber. You can see here, it's kind of a narrow view here, but there's a wider view. The next slide. So the requirements for this were to unconstrain the inner tank length from the length between the holes in the lower airframe. So that's a little bit maybe confusing to imagine, but all of our thrust is guided through the lower airframe piece that's connected at the lower part to the combustion chamber and at its upper part to the bottom of the aux tank. So that length basically constrains the length of the intertank very specifically, and it's unknown to a very high precision what that length is going to be. So we need to be able to, during assembly, sort of have an somewhat adjustable system. We don't predict that it'll have to adjust very much, but it does need to. So we decided to have the system of a rod seal with this 1-inch OD 049 stainless steel pipe that's flared into an AN fitting up there that fits into our upper closure or our forward closure. There in black, you can see our X profile O-rings, and the white are backing rings for those O-rings to ensure the seal is good. So here is a little bit of wider view there, and then you can also see a view of our demonstrator piece. Because this is sort of a novel idea, we wanted to make sure that it worked. So we basically hydrostaticked a piece that we thought was similar enough to prove the design. So we hydrostatic this piece you can see here on the camera to 1500 psi at Zucro. It passed with flying colors for a lead down test. You can kind of see it a little bit more here. The main difference between the two setups is that this is aluminum, obviously, and the actual one will be stainless steel, but we don't believe that the surface finish will be significantly different to challenge the O-ring seals. The main reason we chose X profile O-rings instead of the more classic regular O-rings are because it's got a little bit better characteristics for sealing dynamic interfaces that are meant to sort of slide when you install it and uninstall it. Because they have the 2 points of contact. They also are less susceptible to spiral failure when you're taking them in and out. And they can also accommodate a little bit of Cryotox lubricant in the gap in between the two X's. So that's why we decided on those for the dynamic seal. Any questions on this system or the test piece?
I hate it, but it's kind of clever.
We'll take that.
So Can you use stainless tubing with aluminum fittings?
I'm not sure of that. It might be the case that we have,
I honestly don't know.
I'm not sure either. Okay. Caleb, do you have experience with that? I know, Mr. Rummel used some aluminum fittings from anhousefittings.com.
Oh, not with flared pipe like that.
Not with, okay.
And it's flare 2.
Yeah, flare 2, yeah.
Oh, okay. Yeah, he's right.
It might be the case that we use those aluminum anodized fittings on the upper, up above the run valve, and we might have to use stainless fittings below.
Just to use stainless tubing or aluminum tubing down below.
Above.
There is no
There is
tubing
no
above
tubing.
the run valve. It is a full fitting stack up.
Yeah.
Oh, gotcha.
Yeah. Yeah.
Cool.
So why not get rid of the fitting altogether and just machine this as one part?
So you mean like sort of more like the demonstrator, have it be aluminum, and then just have
Aluminum, steel, whatever you think you need, but instead of having a tube going into a fitting and do that flare and stuff, just machine this part with the right fitting on it.
What is the fitting screwed into?
that's an AN to NPT fitting that goes into the bottom of the run valve. 1-inch AN to PT.
So you
So
could real.
you mean manufacture like a male NPT thread on the end
Mm-hmm.
that goes directly in the run valve. Yeah, so only thing why we wouldn't do that would be just that we don't have experience. But I guess one goal of PSP is to educate its members, so maybe it would be a good experience to manufacture that male thread. So we'll definitely look into that. The only other question beyond that would be the manufacturing time for that versus the actual weight savings on it. That's just a question. I guess.
Yeah, it's just got to not leak.
Exactly.
But
yeah, we'll think about it for sure. Any other questions? See Chris trying to find a reason to hate it.
You just think it was yourself, or is this just a comment?
So actually, I won't take credit for the idea. Cal, one of the former members, actually many months ago, before I think it was in January, came up with the idea, and we never really had confidence in it until we decided to just, we just realized we could just test it ourselves. So it worked. So.
And in the rocket, what keeps these parts? Yeah.
So, do you mind? How do I show a hidden slide?
You have to escape.
Do I have to escape? Okay. I have a hidden slide in case we had questions about this. How do I do slideshow? Yeah. Okay. Cool. So basically, the lower airframe piece, which is like the gray on the outside, that connects to that blue coupler on the top. That orange is our constrained length, and that constrains the blue length very specifically, like I said. So that basically what's keeping it from coming apart is the connection between the airframe to aux tank and airframe to combustion chamber. So this connection and this connection.
So it's the stack up of fittings in the valve itself. Screwed into
the aux tank, which exactly.
Mm-hmm. Not quite. So if you take it right, because if I'm reading this right, if you take the airframe away, the motor will just fall on the ground off.
Yeah. Yes.
It's not constrained to the fittings, right? So you're relying on the airframe.
Yeah, but so the airframe is sized to handle the parachute deployment forces, those shock forces. So it should be more than enough to handle the pressure forces that this one faces. So, but we can calculate that force that it'll be and make sure of that in our further analysis.
I don't think there's any calculating parachute deployment forces, but a lot is the answer. But okay, just make sure your airframe is good because you're relying on it.
Yep.
You're also going to be relying on your stack up being able to be pointing the correct direction, perfectly concentric with everything, right?
Yep. So there will be a very snug fit between that blue coupler and the airframe connected to the aux tank. And then we have these centering rings, which we'll talk about later on the combustion chamber. So centering rings keep us concentric with that airframe.
Sure, but then your valve and everything has to be.
Yeah, true. Yeah, that's a good point.
Okay.
So yeah, we'll, I guess, try to look at any challenge for that. But yep. Moving on, just a little bit of electrical disconnects. It's just something we've been thinking about, because it is flight hardware, so it's definitely more in the distance than the hot fire test stuff. But USB 3.0 connectors we selected because Nostromo used USB-Cs, from what I remember, and USB-Cs are not polarized, so it was possible to plug them in backwards, which would reverse the power and possibly fry components. So they're pretty well, pretty strongly connected, but not too strong. We think that the force of launch won't be able to disconnect them. So we could theoretically manufacture these little 3D printed pieces that could glue onto the side of the airframe with a square hole at the end, and we can play with that angle. Right now, I think it's 45 degrees, but just to make sure it tears out cleanly. So, any questions about this?
USB 3.
So basically, it's just like a USB-A connector, a regular USB with the blue strip. That's like the 3.0.
It has more conductors to support faster transfer speeds.
Gotcha.
So this just gives us, using USB 3.0 type A connectors over 2.0 type A connectors gives us additional conductors for instrumentation valves.
Yeah.
I'm trying to find a reason to hate this, but I think it's actually really clever.
We'll take it.
Good luck.
Thank you.
I hope it's plugged in better than my USB port in my car.
Yeah. Yeah, we may have to decide to, buy them from a good manufacturer that makes, snug. But,
Hey, Simon,
Yes.
if you're gonna use pre-made cables before you get to installing them, cut them first to make sure they're not some weird wire that's impossible to solder to.
Yeah, for the purposes of kind of this little mock-up, we've used an original or just a built cable. The future goal is we'll buy actual like solderable connectors, and we'll have a little custom PCB that'll break those out. So it'll be just the connector port and no cable.
All right, very good. Smarter than I was then.
What was the problem with magnetic quick disconnects? You couldn't find one or just have too much into it?
the magnetic disconnects. I think the issue was just like worrying about the strength connection as far as like the wind blowing or.
There are also, I looked into them a little bit last year, and I was unable to find a super solid vendor for them. I think they're just not very widely manufactured.
The liquid seemed to have one. I think they got it from Mouser.
Okay.
It was pretty good. I can't give you the spec, but it was pretty solid. It shouldn't blow it off.
Really? Okay, interesting. Maybe we'll look into that then. It might be simpler.
Yeah.
And it had like wires too at the end of it, so so it was ready for you to solder.
Yeah. Cool.
All right. Next, we're going to get into the airframe integration. Hugo.
Hi, I'm Hugo. I'm the manufacturing specialist and also the engineer responsible for the coupler design that will join the oxidizer tank to the upper and lower airframe. It's a radix joint design with 45-degree angle bolts relative to the vertical. They're usually 30. We went with 45 mainly because of packing issues. You can see this better in the next slide. It's just so the bolts stick out less. Designed to work at 5,000 psi, 5,000 pound force of. We are predicting our biggest force to be parachute deployment, but it's still up to debate. Our parachute deployment force isn't finalized entirely, which is why we decided to go with a very big number of 5,000 pounds and a factor of safety of 2 on top of that. And one of the other reasons we decided to go with this number is just because of future proofing. As the manufacturing specialist, I want to make these pieces twice. And so giving them a higher safety rating would just mean if something changes in our system architecture, we can most likely reuse them. And also the main cause for failure in our last rocket, Nostromo, was recovery. So not this particular component, but we are trying to prevent that from happening again. So oversizing this component specifically, which is mostly just increasing the number of bolts and pins to different elements, isn't very difficult. So as you can see, there's it's made of 6061 number 6 aluminum. Then it has 6 bolts that pull into both closures for a tank, and then 7 pins that go through the airframe. And the actual idea for this is that we will machine this to be slightly larger than the airframe inner diameter, cool it down, put into the airframe, allow it to expand. We predict that to give us some 10,000 pounds of force. But we're not too confident on both these calculations, the inner like circularity of the airframe and also just the kind of joint they make, how strong it is. So we will be using that mostly to keep the assembly rigid. And once it is fully assembled, we will drill the 7 pinholes through both materials at once and then insert the cleavage pins through them. And this is a view of the actual assembly with the redux coupler and then the tank wall closure and airframe. And that is some of our points of failure. For the bolts, it's mainly through tear out and then the pins bearing of aluminum. We didn't really calculate forces through the airframe just because of how hard those calculations proved to be. We have talked to some professors about the subject, and for now we seem to believe that the very big factor of safety, along with just the general extra force that the heat expansion will give us, should prove sufficient to hold the entire system together. And this will be mirrored exactly almost in the aft closure. Now, any questions?
In the upper, what does the green represent?
Airframe.
And is there actually a gap between your coupler and the airframe?
No, the coupler is the white, the airframe is the green. They physically interact with each other.
Gotcha.
We're gonna chill that way. And then put it into the airframe.
Yeah, Chris actually gave us the idea. We decided to go with less pins than the design you showed, but it should still be plenty. We could always increase the number. The actual, as I said, making those pinholes will be after most of the assembly is complete. We have until then to decide on the actual number of pinholes. And another thing to comment on is the actual length of the coupler. You expressed a worry about the actual rigidity and verticalness, per se, of the rocket, which is why this coupler sits at around 3 inches long. Most of that length coming from that thin section. That is an arbitrary number. It could be made longer. And one of the reasons we just went with a coupler design versus extending the aux tank caps is just the size of the stock and the manufacturing complexity of the operation involved. The aux tank caps themselves are already on the verge of what Bechtel can do, so making them any longer would mean outsourcing them. Any other questions?
I love this design.
It's the third iteration.
It is beautiful design. Sure, it works.
So, how are you gonna get the clevis pins in, those pins, once you've got it together?
Through the other side of the airframe, the tube, the other hole.
You're gonna drill after you put the.
Yes. Yes, it will be assembled and then they'll be drilled together. That is, the idea is that the clevis pins should be the ones taking the force of the parachutes deploying, while just heat, like the expansion of them, should keep the entire thing rigid for most of the flight. And obviously the clevis pins will be tight so that there's not much slack. We will make sure of that.
Caleb, for actually getting the pins in, I think there's gonna be a hatch on that upper airframe piece. So like to actually get the pin in after.
We can also just push our arm through the
I
other
think
side.
that upper is pretty long.
We could,
Oh, so
we-
2 feet. Oh, so 2 feet. Okay.
we can just unbolt the coupler to do the
That too, yes.
clevis pins. And then access them.
Unbolt the coupler in the aux tank, or unbolt the coupler?
Unbolt the coupler from the aux tank.
Wait, are these pins removable?
Not ideally. I mean, you can remove them, but the idea
You can
is.
take out the blue screws to lift it up.
Yes.
Yeah.
To be fair, would be you could take the pins out, but separating the coupler from the airframe would be very challenging. You would have to throw both of them into a cooler that's big enough to support the airframe.
So.
Or brass, right? But this is I'll probably machine as soon as you can.
Yeah.
Put some just to see how it works, just see to understand what kind of tolerance.
But you've got a bolted connection to separate it from.
Yes.
To have access.
I guess my whole thing is why even bother having pins that can be removed if you can't get a socket?
Well, the pins are just because they were easier to find and sort. It's just a pin with another pin that holds it in place. I didn't really bother researching what types of pins would be best for this.
Hey, dial pin in there, right? Just tap it flush, right?
This just seems easier to, but it's just one pin and then another slot into. I will look into the pins.
If you made it where you could get that aluminum pieces separated from each other, you could just glue this together. Or pop rivet it or something where you don't have to worry about pins and slop. Then your tolerancing gets a lot easier.
You need to worry about centering when it's glued, right?
Yes, yes. Yeah. Just be careful. The having the bolts helped a little. Chris is the expert on this, but
So there's a few Swiss teams that do this exact thing, this exact size.
they do. Okay.
That's not the pins with pin in it, but that 90% of us, yeah.
Okay.
And you have no comments on 45 degrees versus 30 degrees for the bolts?
No.
Okay. Anything else?
How are you making this, Hugo?
With a lot of sweat and tears. The ideal way would be to buy tube and machine the tube away. For some reason, tube is more expensive than the actual piece of solid aluminum. So we will mostly buy the entire thing, bore out the inside with a Stellaram.
You'll find the material. What machine? Like you're gonna try to do this on the 5-axis, aren't you?
Oh no, the 5-axis is so terrible. We're boring most of the diameter away in a 3-axis, and then we're chucking it on the lathe. To do especially the tolerancing for the outer wall that has to be fairly tight. We have a 5 thou predicted heat expansion, so we need to get that down fairly well. Only a lathe will give me that, and not even. And then there's a good chance, because of the thinness of the walls, most of the finishing operations for the inside, which isn't critical, will be done on mills.
What about the 45-degree holes?
Those will be done either, yes, on the 5-axis. We have ideas for that we could maybe avoid. There's also a possibility we could do it in one of the 3-axis with the 4th axis enabled. Not likely. It maybe have to be 5-axis. I want to avoid it.
You don't need to pick the axis for that. Wallace does it with the commando machines.
That too, yes. If it's just avoiding the 5-axis in Bechtel is a very, especially for precision, it's very bad.
Another thing to keep in mind when you're machining this, of course, this be a pretty tight tolerance, right?
Yes. We have
take into account the temperature of the part when you're measuring it, machine. That's going to affect, the size when you put it in there. So you really make sure that.
Yeah, we will. I haven't thought through the entire process yet.
Sure.
But that I will put a lot of.
This is great though. This is great.
Yeah, you'll figure out how to make that's a potato chip. Your hydraulic chuck is going to crush it. It's going to chatter. Just make it early.
Yeah, no,
You might have to redo it.
We're making several parts that are actually not this thin, but similarly thin. I have to get used to making parts that are just this inconvenient.
Yep, just make it. It's going to be a tricky one.
Okay.
Jasper. Hello, everyone. I'm Jasper. I'm the lead from Airframe. Just going to talk a little bit about how our airframe interacts with propulsion. So we can see the see-through part is going to be a 4-foot length of G12 fiberglass tube. And at the top, we have, of course, the coupler that Hugo just presented. And then there's a hatch cut out so that propulsion can access intertank plumbing. We plan to 3D print a hatch cover for it, similar to how it was done on Nostromo. Going down a bit, there's a thin motor centering ring we plan to machine out of aluminum. It just functions to hold the motor centered. It just bolts into the airframe. It doesn't carry any load. Going down to the bottom is our boat tail. And this is basically our thrust ring. It's bolted to the combustion chamber via the bolts at the bottom, and then the airframe sits on the lip that's on the boat tail. Here's a little bit more details on the boat tail. So we selected aluminum 6061 likely. We're just gonna use the same stock as the ox tank. And then, as mentioned, we have 6 bolts currently bolting into combustion chamber. We've judged that that's strong enough to handle maximum thrust, that it won't shear through. And yes, as mentioned, it sits on the airframe, and we plan to also use bolts to bolt that into the airframe. It's currently 6.5 inches long. So it being made of aluminum, we do consider that it could be a little heavy. Right now, we're looking at 5 to 6 pounds on the rocket, but we can pick up material. We can deal with it. I think we can handle it. Yeah. So, any questions?
Just make it more or less convenient for your machine.
Yeah.
Let's get some weight off.
Yeah, I think we're okay.
I think
You could remove a lot of the inside profile of wrestling to reduce weight.
Yeah, we can make that converge at a different angle. We just need enough material up there to.
No, just remove.
Okay. Yeah, that works. Yeah, we can work with Hugo also on how we can manufacture this. Cool.
Is it?
Guys in a different color?
Oh yeah, that's something we talked about. Yeah, we could do something cool.
Is it straight because it's going supersonic?
Straight?
Like it's not like an ellipsoid, or it's like a straight line between the two.
Oh,
like
I haven't done detailed aerodynamics and analysis of this. Just most boat tails I've seen have looked something like that. Yeah.
Okay. So aerodynamics question.
Yeah, that's true. I should research that. Okay. Good.
Hey, Jasper. And so I'm going to talk about our ground support equipment. There you go. Why did it go to the bottom? I'm sorry. So the ground support equipment of Nostromo, Spectre is going to be using we're going to be loading from 2 nitrous K bottles, a helium bottle, and using 100 psi nitrogen as our pressurant. We're going to be boosting the flow of our nitrous into the flight tank using an air-driven liquid pump with a 25-to-1 pressure ratio. The control of fill of the nitrous is going to be controlled by our nitrous fill valve, and the control of helium fill is going to be controlled by the helium fill valve. We have a dump valve that is integrated into the ground support equipment that can dump both the helium and nitrous lines, and if the quick disconnect is still connected to the vehicle, it can also dump the flight tank. We have installed 1500 psi relief valves on the helium and nitrous lines, and we will be regulating the tank pressure supercharge using the regulator that's on the helium line. So this will be set to 1000 psi. And yeah, like I said, we'll be using 100 psi nitrogen as our pneumatic pressurant. So we'll be running the Habitums and the QD actuators off of this nitrogen source, and it'll be regulated by this pressure regulator up here. Does anyone have questions about ground systems?
2 nitrogen tanks to run the pump and the actuators. I guess it depends on how much nitrogen you can pump.
Right. One of the variables is how long we have to run the pump for to get our nitrous fill, which is why, to be conservative, we were going to integrate 2 bottles. And if we found we didn't need it, we can eliminate it. But this was like the conservative side of it.
What kind of a pump is it?
It's a air-driven liquid pump. So it uses like a piston ratio to drive the
A diaphragm pump?
I don't think it's a diaphragm pump. It has a piston, and it uses a piston ratio where it uses the 100 psi inlet pressurant, and it outputs up to 25 times your your inlet pressure.
Yeah, it's literally just two pistons hooked together. There's a slide with two pistons and one is 25 times smaller than the other.
Is this what was used?
This was used for Nostromo for the last rocket. We used it on the launch.
Okay, we used an air compressor to pump that thing.
Sure.
It was too forever. You know, you had to recharge and go again. So
Right.
I mean, you can calculate, right?
Yeah, we can.
You know the volume of your flight tank.
Yes.
And you know the displacement of the high pressure piston.
Right.
As well as the displacement of the, so you can calculate, estimate the number of cycles that are required.
Right.
Which tells you the number of cycles of nitrogen that are required.
Right. Okay. Yeah. So I'll run those calculations.
And what part of this is not named yet?
So.
And where is this?
So this is. Sorry, what do you mean by where is this? Like, where's the current hardware? Or so the current hardware is in Potter in our storage area, but we have it was the Havoc and Nostromo GSE cart. And currently the nitrous line is assembled. The helium and nitrogen lines are not assembled. There are a couple of features that we need to add to the nitrous line, like the PT that's off of the nitrous bottles. But besides that, the nitrous line is almost fully assembled.
Where are you guys cleaning it as you put things together?
We'll clean out the fab shop. So the plan is to.
You're just building it up right now.
Right. So we haven't started to build it up right now. It's just all of the leftover pieces that are from the Nostromo launch. And then as we rebuild it, we'll move the GSE to Zucro and we'll clean in the fab shop.
Another thing to take into account, the issue up to Mojave, the dust gets everywhere. So just make sure you're taking precautions. Add a filter, if you need a filter somewhere, right? Just so maybe it's over the dirt.
Right. Yeah. So currently we have filters off of all three of the supply bottles. I think we were considering also that like inline filter that you mentioned for when the quick disconnect comes off. We were doing some research on that, but I think
But mufflers on your vents.
Right.
Yeah, make sure all your pneumatic stuff has mufflers in the vents and everything. And then why does the flight vehicle have two TCs?
So we can integrate two TCs, but it's likely that the forward TC is not going to be integrated. The critical one is the aft TC to measure the temperature of the liquid nitrous.
Okay, and will you need that TC for flight?
No.
You'll be able to know.
So.
You'll be able to know your nitrous state without it. Because you're gonna have helium on top of it.
Right. We may actually.
I think we need to calculate our loaded mass.
Right. So we may need that TC on the flight tank for flights.
Where's your avionics?
The avionics is forward of the tank.
So do you have a path for wires to get from the aft end of the rocket to the forward end?
Oh, you're saying, so the TC will be routed out along with the other electronics that are in on the aft end of the tank. So like the run valve. So we'll route that TC like around near the other electronics that are being routed out of that side of the tank.
Separate disconnect, separate power.
Right.
The avionics and the instrumentation for the propulsion system are completely isolated from each other, different systems.
So, quick thing, your TC in the upper tank's not gonna. It has never worked in the past. The TC in the fluid might, but thermocouples don't love going through electrical disconnects. So make sure however it's gonna fly is how you have it set up for your test fire.
Okay.
Instead of just running the wire out of the fuselage.
Right. Okay. Yeah, we'll have to make that more robust than it is now, or more well defined.
It might work. Just it would be sad to get to Mojave and not have that sensor working through the disconnect.
Right.
Fly.
So the pressure transducers that you're showing on the combustion chamber.
Yes. One of them measures the pre-injector pressure, and one of them measures the post-injector pressure. This is to better characterize the injector during testing. Neither of those are going to be used during flight.
quickly to elaborate on what Caleb mentioned, thermocouples, they don't like connections between dissimilar metals, right? Because thermocouples take measurements by generating a voltage between two dissimilar metals that is under some temperature. So if you have other junctions like interconnects, whatever, be very picky about the type of interconnects you choose so that you don't have two different types of metals contacting each other and creating what is essentially a second thermocouple in series with your first thermocouple.
Gotcha. Okay. That's good to consider.
Send to a cell conditioner before we send it over.
Right.
If you already have the PT ports on there, I would always champion for some sort of data recorder on the
Okay.
What happens to the rocket. I mean, you spend all this time getting this rocket, this engine's super efficient and whatnot.
Right.
And then showtime, it's like, I have no idea how efficient the engine was, right? So, what we did in the past, is a Raspberry Pi. And there's a company called Measurement Computing that sold a hat for the Pi. And it was able to take like 3 or 4 PTs, and then it had 3 or 4 slots for thermocouples with a conditioner on. Wow. So all we did was, splice the wires from PTs and had it one go outboard to the GSE, the other go to the Pi, and I just record. That's all I did was record.
Okay. Yeah, we'll definitely look into that then. If we think that we can do flight data acquisition, we will. Just it wasn't a requirement for the flight data acquisition.
If the PT's already be on there.
Yep.
$50, you can have data.
Yeah. Okay. Oh, shit. I'll make soon. There we go.
So my name's Thomas.
I'm Horace.
We're part of the K bottles team. And so the main problem we were faced with is traditionally with the K bottles, with the nitrous oxide K bottles, with them in a traditional arrangement, yeah. We would have to use dip tubes to access the nitrous oxide, which would leave a little bit of nitrous oxide inaccessible. So our solution was to invert these K bottles upside down to be able to access all of the nitrous oxide. So this K bottle stand is able to secure both K bottles in an inverted position on either side of the vertical central support, which these K bottles will be chained and strapped to. This K bottle stand is made of aluminum 1x1 inch 80/20 rails because of its ease of assembly, minimization of manufacturing, and also its strength. So the way we would load these bottles is by taking off one side of the legs, which should be easy to take off. So we would then put this system on its side and then lower the bottles into their respective positions, chain and strap them, and then raise the whole system up again and reattach the legs.
Yeah, that's good. Questions first.
Are there any questions yet?
Before we go into like potential tipping issues.
How are okay. How much does it weigh?
Each or the stand itself.
I mean, when you go to stand this up,
yeah,
how much weight's gonna have to be lifted?
Each bottle should be around 50 pounds each. 150 pounds. Okay, yeah. So in total?
For each one.
Or for each one, 150 pounds each. Yeah.
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 So you guys wanted to lift 300 pounds?
We'll have multiple people on it.
So we plan on probably attaching like a rope or maybe even using the rat strap that will be around the two. It's like sort of pull as well as lift. And because you take the legs off, the moment's a lot lower. The moment ideally will be lower because it'll be close to the center. But so you'll have some leverage on it, but you won't need to like physically lift it up into the air. So yeah, if you get a couple people or 2 to 4 people and some straps, I think you can tend to. Is there a way that you can potentially just pin in the base? So it's tipping on that base, and I'm assuming you're going to stake this in the ground.
Yeah.
Once you get it
tipped up, is there a way that you can actually stake that rail that's still fixed on the ground, that way it's not sliding across the ground and fighting you as you're trying to tip it? I'm just trying to think of ways.
Yeah, that's something we can do.
I think it's a reasonable design. I don't like your chains. I think you need to have an actual 80-20 frame that the bottles are in. Right?
Yeah.
So when this thing's laying down, you've got 80-20 running crossways under it. So when you're picking it up, the bottles actually move together. Where here, if someone's picking up on a bottle more than the other bottle,
Yeah.
keeping it all aligned and together when you stand it up is going to be kind of challenging.
Yeah.
So I think making your whole, bottle frame out of 80-20 might be to your advantage.
Okay.
It's not pictured on here, but I believe you guys were also planning to use like a ratchet strap to hold them together. So that'll help make everything a little bit more rigid, but we can look into what.
Well, I'm basically picturing your vertical two on each side. You can point to it.
Just like here?
Yes. Run those up the entire length of the bottles.
Yes.
And then you can have another cross member under them, on each side, and so they're completely sandwiched.
Okay. Yeah.
So that they're held in there in a more positive way when you're rafting it and taking it down.
Right. It's cool.
So-
Yeah, so on your bench mounts, I think they're called, or table mounts, that they rack it via table or bench.
Yeah.
Use a couple of those for each of the mounts, then kind of straps on those.
Reverse, you try and tilt it down. Of course, you can tilt it up, right, but like, trying to keep it from like getting away from you and just falling into somebody.
Probably have people on both sides. Yeah.
Steel toe shoes.
Yeah.
I'm joking with that actually. And how do you plan on moving it in space? So you're gonna get it off, I guess you're gonna put the bottles on when you're next to the pad, right?
Yes.
All right.
If you do what I was suggesting with respect to those, you could have a cross member that sticks out far enough, and you could have two people on each side. Make it easier to handle.
Bring a rope attached to that.
Nah, no rope.
No.
Just, 4 people can handle 300 pounds. That shouldn't be an issue.
So I know you guys are gonna do some tipping stuff here, but like those bottles need to be positively retained. So like if they need to be ratchet strapped in, it needs to always have a ratchet strap with it. Like it's gonna be 4 in the morning. It's gonna be 0 degrees. The ground's gonna be covered in ice. Like, I'm not to be negative now, but just make sure K bottles need to stay safe. Even if it falls over, even if so just be 100% sure.
McMaster sells 2-banger bottle restraints, right? You could integrate that into your 80-20 very easily.
Yeah, that would be great. Just those stems cannot come off.
Yeah.
So cool. And you might want to triangulate that base a little bit. Just test the crap out of it.
Yeah, with it being orderable, we can easily get it in and start assembling it, just testing around to see how it is structurally and making sure nothing is wrong with it.
Yes, with the caps on.
Right.
Yeah.
Okay, so just going into tipping issues, potentially worries, not with Zucro testing, but with Dairy Farm or the FAR launch, we're concerned about if the stand isn't actually perfectly level. Without ways to mitigate it, but just to make sure, like, just for this current design, with any extra things keeping it perfectly flat at those potential places there could be tipping issues. So we decided to see how much force on the top part, which would be the worst case scenario, would result in it tipping over. And we wanted to keep it at least able to withstand over 200 pounds of force at the top. And we found that at 8 degrees, this would be perfectly fine. It'd be able to withstand 200 pounds given the current leg length. But on it and on its own, it'll tip at 14. And these are just some other potential scenarios discuss potential issues with tipping and potential mitigation solutions we thought of. Cool, thank you.
So hi everybody, my name is Nick. I'm the data and control specialist for the prop team. And currently this is our DAX. It is housed in this black box container. The way that we reconnect it to the ground systems cart is with these wire connectors here. It's a simple plug and play, and they have secure screw connections with them, so they shouldn't come undone. The hardware that we're using, our controller is a USB 6343. We have a backup of a Myrio just in case the 6343 doesn't work. We have signal conditioners for our TCs, our PTs, and our load cells. The software that we're planning on using is for the USB. We're going to use Zucro's LabVIEW. The Myrio has its own LabVIEW. I would like to use Zucro's LabVIEW because that's a little bit more user-friendly compared to the Myrio's one. So as you can see, it's a big black box. We're planning on painting it white eventually. And as far as a cooling solution goes, we have two Noctua fans, one pushing air in and the other pushing air out. These fans have enough CFM within them to completely cool anything that's within the box. There's also some air conditioning filters there, so when we go out to the Mojave, no sand will ever get into this box. Right here is a wiring diagram for how this entire DAX is wired up. We start from power coming from an outlet and is then thrown into our power converter here, since our instrumentation requires 24 volts inputs. So we're able to provide our instrumentation with whatever power they need, while the rest of our stuff can get powered off of 120 volt AC. So we have our relays, which serve as our AOs, and our signal conditioners, which serve as our AIs. And this is pretty much how our entire DAX can communicate with our GSE, and we can get data from the rocket back to us. So, any questions?
We had a lot of trouble getting the USB DAC to control PWM signals.
Yeah.
You should see, there's probably someone here that knows how to do that.
To control what signals?
PWM, the run valve needs a PWM pulse width, and the USB DAC doesn't support it natively. It was a weird, it like emulates it in software and we could never get it to work. That's why we switched to a Myrio. Just, yeah.
I mean, I don't know exactly what, because PWM signals vary a lot on a case by case basis, but you know, you get something for like a low voltage PWM signal, you could get like any kind of off the shelf microcontroller, like an Arduino or something, and get creative and wire that in. That starts to get a little sketchy. You definitely want to test it, but there's ways to use an off the shelf microcontroller and a MOSFET or two to get a good PWM output. So long as you can interface that with your USB DAC.
So it's a servo motor that you're using to.
What about servo motor?
The servo motor.
Okay. And it's the servo motor. Those are generally used on like fifth scale like monster trucks and stuff like that. So I'm sure there's some sort of commercial solution we can look into for controlling them that is reliable and relatively expensive. So we can look at what they use on like RC cars for that.
So are you using a limit switch to indicate the limits of travel for the valve, or are you actually counting pulses to the servo motor to know when you moved at 90 degrees?
I think we would be more of counting pulses. It's just like a simple digital output, so it's either open or close.
Well, you're not really counting. You're not counting anything. The servo has an internal encoder, right? So like if the servo were to jam, you wouldn't know about it. You're just feeding it a signal that says, hey, I would like you to be here, and it's going to do its best. But if something goes wrong, it loses power, you don't have any valve state indication. I haven't worried about it in the past, but it would be better to have it. And then also a lot of those high powered servos are digital and they go to a home position when they turn on. So you need to make sure that home position is where you want it to be, that if your system were to change state, it doesn't open the valve or something. Just to, yeah.
Are you gonna have how do you make certain that the run valve can't open with a screwy method of controlling it? The picture that was just painted didn't really have a lot of confidence about operation of the valve.
Yeah, we're gonna probably look into that. Like Chris said, it's probably one of the first things we can buy, to start testing. So we'll probably start that testing as soon as we can and try to figure that out.
I mean, is it a case where you could put a relay, a mechanical relay between things that you use a digital output signal from the DACs to enable the control?
Possibly could be, yeah.
Just, yeah, like the last one we used, we bought a specific servo at the home position and we set it up that the home position was closed so that if the servo lost power, got a bad signal, it would just try to stay home, which is closed. And then if it did get a weird signal like noise, it had digital filtering on board where if the signal was not a clean signal, it would just reject it. So that it wouldn't try to open if you got a bad connection or something. Like it had to be a very specific frequency and pulse width and stuff. And so we did all that crap. And you can buy modules to send that signal to it. Just again, it needs to work right.
But Scott, I think your suggestion of a relay to lockout servo control is a good suggestion, and we'll look into implementing that.
It's a suggestion. You decide whether it's good.
Oh, yeah, and the DAC had that, Nick. I don't know if you left it. But it only powered up the servo in the last few seconds in the auto sequence before sending it the signal to open.
That's what I was looking at in the lab view. So
Yeah. So it would power the servo on and then it would send the open command a few seconds later.
I see.
That's what that relay was for.
Got
That's
it.
also so that if the servo does end up near home but not at home, it won't sit there and jitter and overheat.
It's a nit, but the relays are used for digital output. They're just on and off, not analog output.
Yeah, that's supposed to say digital, not analog.
Are you gonna use, do you have any AO signals you're gonna use?
Probably not. I know we're looking into that, so that way we can partially open certain valves, but currently, there's no real reason, just open and close.
So you're planning a load cell on the launch rail?
So the current plan is to do our, to not integrate a load cell on the launch rail, but to have some sort of measurement system, whether it be a scale and a camera or a load cell on the propellant bottles, on the K bottles. And then also monitoring the thermodynamic state of the tank, the nitrous in the tank, using the PT and the TC that's on board, to confirm that we've loaded propellant.
If there's enough nitrous on board to have liquid present. How are you going to use temperature and pressure to determine how full it is? Right, if there's any liquid present and the system's in thermal equilibrium,
right,
you're gonna have the same pressure regardless of how full it is.
Right. Yeah, so we'll primarily use the measuring the weight of the bottles.
So you'll be looking at the change in weight of the K bottles.
Correct.
So did did you make that a requirement to your team that's doing the bottle holders?
No, but it's gonna be. It's oversight on my part, but yeah, that is the challenge of doing the loading on the launch rail where we're not gonna encounter that at Sucro, so it's kind of
No, it makes sense that you did it.
right.
That's a little wrinkle.
Right.
Yeah.
Should also tell the K-bottle team about the heating jackets or however you're gonna control the K-bottle temp before they change their design. Make sure it'll still fit.
Will do, yes.
Do you need it with the pump?
It helps a lot. And it depends on where Brian wants his nitrous state to be. If he wants it warmer than ambient.
Right. The primary challenge is testing, if we do our test campaign like January, February, where this is gonna be lining up, is that, yeah, well, the supply bottles are planned to be heated. We're working through heating solutions. I know in the past, Scott, we borrowed a heating jacket from you. I didn't know if we were gonna talk to you about that again and see if we had any other like solutions that we could use.
Those heating jackets are robust in some.
Completely opposite, we are 110 degrees outside.
We're also working on a cooling solution for the flight tank. Insulating and cooling, active cooling. But it's not fully developed yet. So we're gonna move into just like general questions now, or if you had any other specific questions about any other component. But that was our presentation.
That's very nice. The design of your fuel grain and the conditions for your fuel grain.
Yep.
You need to come up with how to vet that design.
Right.
Given that you're trying to push the envelope.
Right, well, we'll look at first, seeing how we can tune our startup thrust. And then also if we're going to be expanding that, the fuel grain itself with how we're gonna change the liner will become a little wider. We can consider opening up the port a little bit to lower the mass flux in that region. And we can consider lowering our initial oxidizer flow rate. But we'll play around with the simulations to see what, like what's.
Well, I don't know that there's any simulations you can. I think you need to look at what has been demonstrated.
Right.
With that are fairly specific to your column combination and chamber pressure, right?
Yes, yeah. I just meant as in like our propulsion top level simulations to see what the best way is to lower just our total mass flux, because it's just computed in that.
But you'll have to all I meant was do something else first to figure out what your target is.
Right, exactly.
You guys gonna go over the well, that's nice, but like the recovery and rest of the rockets.
The plan is to have some sort of like full rocket design review later this semester.
When's the target launch?
Target launch is for summer of next year. That is if we can stick on our current ambitious timeline. But so the timeline would be we finish our design reviews this semester, get into procurement late this semester, early next semester, testing at Zucro January, February, March, dairy farm launch hopefully before the window for doing it at the dairy farm closes. And then if all bodes well, we go to FAR in the late spring, early summer.
So to hit that timeline, you got a lot of machining to do.
Yes.
A lot of complicated parts.
We have a lot of parts to make. We have a lot of things to get.
Your fins just epoxy or fiberglass onto the airframe.
Jasper.
What fiber?
They just fiberglass on the airframe, the fins.
Oh yeah, it's we're learning how to do project edits. Yeah.
Awesome. Thank you guys very much.
Nice job, gentlemen.
Thank you.
Thank you very much. Thank you very much for your time. You bet. Really appreciate it.
People on Zoom, there's a link on the handout that I gave.
I'm sorry.
There's a link to a feedback form that's on that sheet. So if you have extra like feedback that you wanted to include or extra questions, you're welcome to put that in there or not. I do not care. I can sit here and look at the chat for a little bit longer if anyone has last minute questions.
I think that was like,
That was probably the best video on
the perfect level.
But thank you guys very much for
allocating design, and still making sure that we.
Matt, I know prop isn't really your thing, but we appreciate your time and coming down here. We know it's like not your interest field, but it was awesome seeing you. Blake and Sarah, thank you for coming by. It's good seeing you guys. And Caleb, of course, as always.
No problem. Best of luck. I might give you some more feedback later, but I think that's all I got for tonight.
Great. Thanks so much.
Yeah,
great job, guys. It's been great so far from what I've seen. So this is really, really good progress building off what Caleb was able to accomplish at the end of last year.
Thanks, Sarah.
Thanks, Sarah.
I guess final thought, I can't stress this enough. Holy crap, you guys are like way ahead of where Havoc was when I was on the team. It's
what we
like night and day. Like, anyway, glad to see you're in good shape.
That warms my heart. Thank you, Matt.
Yeah, congrats, guys, and I'll be sure to fill out the feedback form. So,
awesome. Thanks, Blake.
Thank you, everybody.
Thank you guys for your time. Have a good night.
Hi, Ritz people. That went really well. Thanks for all your hard work. That was all you guys who made that happen.